In this section, we're going to learn about EIGRP for IP version 4. To form an EIGRP peering, EIGRP must be enabled on routed interfaces between routers on a common subnet. Once EIGRP is enabled, hello packets are sent out as discovery messages between routers destined to multicast address 224.0.0.10. Once all of the EIGRP neighbor adjacency requirements have been met, an EIGRP adjacency is formed, routing updates are sent between the routers, then EIGRP can be used as a dynamic routing protocol to advertise networks between routers. EIGRP uses autonomous system numbers to create boundaries for routing advertisements. These boundaries can segment EIGRP domains so that you cannot advertise routes between EIGRP networks unless you actually were to configure routing redistribution. EIGRP has an internal administrative distance of 90. If we look at an example of what would happen if R3 learned the same route from two different protocols, including EIGRP, since EIGRP's administrative distance is 90, which is lower than OSPF in this example, it would be considered to be the best route from R3's point of view. One thing unique about EIGRP when compared to RIP and OSPF is that it has an external administrative distance of 170. The external administrative distance comes into play when routes are redistributed into EIGRP. So for example, if R3 were to learn a route from OSPF and then redistribute it into EIGRP, then that route would have an administrative distance of 170. So we're only going to use the internal administrative distance of 90 that we previously discussed if the route was actually generated from the EIGRP autonomous system. To calculate routed paths, EIGRP uses diffused update algorithm, also known as dual. With this algorithm, topology tables are created on routers. Once the algorithm is ran, it can actually create the routes in our routing tables for EIGRP. The metrics that EIGRP uses by default to calculate its best routed paths are bandwidth and delay. Bandwidth and delay are enabled with the default K values that are used for EIGRP to determine what values to use in its routing formula. So as you can see here with the example of the EIGRP composite metric calculation, it has bandwidth and delay used in its formula. With the next few examples, you'll see how with this formula, EIGRP can calculate its metric value. Let's take a look at an example of how we can calculate the EIGRP metric. So which route is best to get to the 10.3 network from R1? First, let's take a look at the path via R2. So if R1 were to calculate the routed path to R2 and then to R3, the first thing EIGRP needs to plug into the metric formula is the lowest bandwidth speed in the routed path. So even if you had one 10 gig link and one 100 meg link, you have to use the lowest bandwidth speed link in your calculations. So in this example, if we look at the speeds of the links from R1 to R2 to R3 to get to the 10.3 network, 10 megabit per second is the lowest bandwidth in that path. So we'll take that value, plug it into our formula. Next, we have to add the cumulative delay in the routed path. So that's going to be the delay values on every outgoing interface within the routed path. So here we have a delay of 30 if we add up all these outgoing delays. Before we plug the delay value into our formula, we have to divide it by 10, which gives us 3. Pull up our calculator here to do the math together. I have this calculator set to scientific mode for this calculation. So let's start at the top here. We're going to do 10 to the 7th. Then we're going to divide that value by our bandwidth in kilobits per second. So we had 10 meg. So instead of writing out actually 10 megabits per second, which would be 10 and 6 zeros, we're going to write out 10 and 3 zeros, and that would be 10 meg in kilobits per second. That gives us 1,000. And then we're going to add our delay, which is 3 here, so plus 3 equals 1,003. And then finally, multiply that value by 256, which is going to equal 256,768. So there we go, we have our metric from R2 to R3. Now let's figure out what the path would be from R1 to R3. Here our slowest bandwidth link is 100 megabits per second. Plug that into our formula, and then our delay is 100 plus 10. So we'll take 110 divided by 10, that gives us 11. Bring the calculator up again, so we'll do 10 to the 7th divided by 100, 1, 2, 3. It's going to give us 100, add our delay of 11, multiplied by 256. It's going to give us a metric of 28,416. So there you go. Since the lower the metric, the better in the EIGRP, the path to R3 would be the more preferred route in this example. Don't think you have to know how to calculate these metrics. It's just good for you to understand how the bandwidth and delay values can manipulate your routed paths. So as long as you can remember that it's going to be the sum of the delay in the routed path and then the lowest bandwidth link speed in the path, then you'll be good to go for what you would need to know in the real world and as well as for the CCNA exam. Once our EIGRP metrics have been calculated, EIGRP classifies metrics as feasible distance and reported distance. Feasible distance is a local router's metric to a route, while reported distance is a remote router's metric to a route. Let's take a look at an example of how we would determine a feasible distance. So what is R1's feasible distance to get to the 10.3 network via R3? That would simply be the local metric that we calculated in the last example. So our feasible distance for that path would be 28,416. Now let's take a look at what a reported distance is in this diagram. So from R1's point of view, it learned the 10.3 route directly from R3 and from R2. So R2's local metric or feasible distance to get to the 10.3 network via R3 is 26,112. When it advertises the 10.3 network to R1, it would advertise its reported distance, which would be the same as its local metric to get to that route. So a reported distance is just what a remote router is telling us its feasible distance is to get to that route. Once the EIGRP has its feasible distance and reported distance values, then we have to know what our successor and feasible successors are for EIGRP. A successor in EIGRP is just basically the best EIGRP route. A feasible successor is the best backup EIGRP route, and it must meet the feasible condition and have a RD less than the successor FD. So let's take a look at what we mean by successor and feasible successor. So in this diagram, which route would be R1's successor route for the 10.3 network? Our best local metric, our feasible distance on R1, would be considered to be our successor path. Now, which route would be R1's feasible successor route for the 10.3 network? Well, since R2's reported distance was 26,112, which is less than our feasible distance for our successor path of 28,416, it meets the feasible condition of having a RD less than the local router's successor FD, and it can be a feasible successor path for the 10.3 network. The benefit of having the feasible successor path is that it can allow for faster convergence when it has a feasible successor path. For timers in EIGRP, it uses hello and hold down timers. By default, EIGRP hellos are sent out every 5 seconds. The hold down timer by default is 15 seconds, and it monitors these hellos. So if EIGRP routers have a link go down and they do not receive hello messages before the hold down timer expires, then the neighbors would be considered to be down based off of the hold down timer expiring for that neighbor's hellos. EIGRP, being a distance vector protocol, also uses split horizon just like RIP does to prevent routing loops. If you can remember from the RIP section, split horizon simply means that a router will not advertise a route back out the interface that it learned the route from. EIGRP has the ability to advertise default routes to the rest of the network. The most common way to configure this would be to have a static default route on a router and then just redistribute it under your EIGRP autonomous system configuration.